Hi, my name is Bin Fan.
I am a PhD student at Northwestern Polytechnical University, and will now present our paper Context-Aware Video Reconstruction for Rolling Shutter Cameras.
The CMOS camera with a rolling shutter mechanism is becoming more and more popular.
The rolling shutter camera is exposed row by row sequentially. Therefore, the images captured by a moving rolling shutter camera will have geometric distortions, such as strew and wobble, which is known as the rolling shutter effect. Fortunately, this exposure mechanism hides rich spatiotemporal information in rolling shutter images. Nowadays, it is becoming increasingly attractive to inverse this imaging mechanism to generate a latent global shutter video from two consecutive rolling shutter images. Inspired by the task of video frame interpolation, we redefine the rolling shutter temporal super-resolution problem in the temporal dimension. Given two rolling shutter frames at adjacent times 0 and 1, we aim to synthesize an intermediate GS frame corresponding to any time t, where t is greater than or equal to 0 and less than or equal to 1. In particular, the middle scanlines of the two rolling shutter images correspond to time instances 0 and 1, respectively. The geometry-aware inversion proposed in ICCV 2021 warps rolling shutter frames directly. Hence, it suffers from two limitations. Firstly, masses of black holes, as shown in the orange box.
This is a common issue for warping-based methods due to the occlusion.
To maintain visual consistency, a cropping operation is used to discard the holes, but may degrade the visual experience. Secondly, noticeable object-specific motion artifacts, as shown in the red box. When recording dynamic scenes, the moving objects violate the assumption of constant velocity motion, resulting in severe motion artifacts. To deal with these problems, we propose CVR, a compact and efficient rolling shutter-based video reconstruction framework.
It consists of two modules. First, two global shutter frame candidates are generated by the motion interpretation module. Then, a global shutter synthesis module is attached to perform motion enhancement and contextual aggregation. In ICCV 2021, Fan argued that the bilateral motion field can be generated by scaling the optical flow field. In this equation, the bilateral correction map can be learned by an encoder-decoder network due to the complexity of pi v. Here, pi v involves the complex rolling shutter geometry.
As shown in the figure, we observe that the effect of the ratio of pi v to h is not significant. So we further propose an approximated version by neglecting the parallax effects.
This approximate model is independent of the image content and can be predefined. Based on these two kinds of formulations, we can get two forms of bilateral motion fields by scaling the optical flow. One is to learn the correction map with the network, called NBMF. The other is a direct calculation, called ABMF. Note that NBMF has better performance than the simpler ABMF.
Finally, after obtaining two candidate frames by forward warping, we further improve the final flow fields by learning bilateral motion residuals, while estimating bilateral occlusion masks to guide the final frame synthesis. In our experiments, our method achieves advanced performance in removing the rolling shutter effect. This shows a qualitatively corrected example.
Our method recovers visually more satisfying global shutter images.
Combined with the GS frame refinement module, our ABMF model is able to provide concise and tractable benefits for global shutter video recovery, while NBMF can produce better results due to better initialization. We show global shutter recovery at times 0, 0.5, and 1, respectively. Our method can adaptively and efficiently reason about complex occlusions and temporal abstractions, leading to visually more satisfactory reconstruction results. Thanks to efficient context aggregation and motion enhancement, our method can generate a smooth global shutter video with more details and fewer artifacts. At the same time, our method also generalizes well on unseen real data and can generate a coherent global shutter video. In conclusion, we redefined the rolling shutter temporal super-resolution problem in the temporal dimension. Then, we proposed a simple yet effective bilateral motion field approximation model. We developed an efficient context-aware global shutter video reconstruction framework and achieved the best performance.
That's all, thanks.